Or an overestimate? Under, yeah. So it's the correct answer would be adding those infinitely many positive numbers together. And I stopped at 4. But, which S did I use here? So, which R is the remainder for S4? Is it R4 or R5? R4 is the remainder for S4, which starts at R at 8.5. So we know that R4 is between two integrals. And I want you to take a moment and decorate these two integrals with the appropriate lower bound. Gentle reminder about the error bounds. R is smaller than the integral from n to infinity, and bigger than the integral from n plus 1. So for our particular example, what's the lower limit on the right? 5, and the lower limit on the left? So we know R4 is between 0.20 and 0.25. So back to my original series is there's the S4, and R4 is what I have left. Huh? No. So remember, R4 starts at the 5th term. So R4 is the remainder for S4. So what happens if I add S4 plus R4? If I add those two together, what do I get? I get the entire sum that I'm looking for. I get S infinity. So I know this. And then, if I add S4 to all of this, well, S4, we worked out as 1.4236. So if I add 0.2 to that, S4 plus R4 is the sum of the entire series. That's the S infinity. And then this is 1.67. So by having that upper bound and lower bound for the error, is I've got a range of possible numbers that the answer can be. That's not too surprising. I've got the 1.4 as my estimate. And then, as I knew that was an underestimate, and the actual value is somewhere between 1.6236 and 1.6736. So let me draw a picture of that. The answer to my question is going to be some number in this range. If I had to guess one number, what would be the best guess? The best approximation is going to be the one right in the middle, which is the average of those two. So I don't know if that's an underestimate or overestimate anymore, but that is going to be a lot closer than my original estimate. So knowing the range of the error Oh, so actually, let's put it this way. If I knew my approximation and I knew the error exactly, then I would know the exact value I'm looking for. Instead, I know my approximation, I can compute that. And I've got a range of possible values for the error. That gives me a range of possible values for the real value. And then, if I had to pick one number as an approximation, it's going to be one number in this range. And the best I can do is by picking the middle number. You guys excited to go on to the next section?
No.
Really feel mathed out? Right.
Okay.
So we had to integrate. And to integrate something like this, we split it up. So same idea. If I give you an expression like this, it's you've got a way to use partial fractions to break it down into simpler fractions like that. So I'm not going to go through the whole process. I'll give you a gentle reminder. So you're going to look at this as 1 over n times n plus 1. And you're going to break this down into 2 fractions. One of them is n, one of those is n plus 1. What do I put in the numerators here? What's this numerator? In this numerator. And then we talked about the whole process. What you're going to get is that A is 1 and B is negative. Infinity does strange things, though. So remember how we talked about never in your addition career did you add up infinitely many numbers in elementary school? So do another example to show you it's not quite as easy as it seems. And to do that, I'm going to have to give you a gentle reminder about how arctangent works. We talked about this briefly in 7.8, the improper integrals. So remember the tangent graph is what we call the principal branch. It is some snake-like curve between negative pi over 2 and pi over 3. And then the inverse function is really just switching inputs and outputs. So x becomes y and y becomes x. So the inverse tan graph is just this one reflected above the line y equals x. And what I'm going to need for my next example is arctan of infinity. So what's arctan of infinity? Yeah, so if I kept pushing this out all the way to infinity, I would expect I would do. I'm going to be referring back to this graph a couple times for my next example. Right now, I'm going to tell you that it does converge, and I want to find this out. So let's write this out. The n equals 0 term is arctan 1 minus arctan 0. Agree with this part? Let me show you something kind of weird. is arctangent is an increasing function. So here's 0, here's 1, here's 2. Arctan of 0 is down here. Arctan of 1 is there. Arctan of 2 is even higher. So is arctan 2 minus arctan 1 positive or negative? Positive. And you see that all these terms are going to be positive? Does this look like a telescoping series to you? Does the arctan 1 get canceled out? Does the arctan 2 get canceled out? Is the arctan 3 going to get canceled out? What's going to survive? Minus arctan of 0. And what's the arctangent of 0? 0. So how can I add infinitely many positive numbers together and get 0? Is that some weird? Yeah, sure. The solution is this is not the answer. Let's talk about what the answer really is. I'm going to refer back to arctangent again. Assume we know it now. So the real way to understand what's going on with an infinite series is to do the sequence of partial sums. S1 is arctan 1 minus arctan 0. S2 is arctan 1 minus arctan 0 plus arctan 2 minus arctan 3. That's the first 3 terms. And I will erase over there while you're taking it. Remember the sequence of partial sums is S1 is the first, S2 is the second, S2 is the first 2 added together, S3 is the first 3 added together. So if I simplify, what does the second one come out to? What are the survivors? Okay, so this one is, nothing's going to cancel out that arctan 2, and nothing's going to cancel out that arctan 0. And the third one, S3, is going to be arctan 3 minus arctan 0. And S1 is arctan 1 minus arctan 0. So what do you think the formula is going to be for Sn? So there's going to be something that survives. When it was S3, it was arctan 3 that survived. When it was S2, it was arctan 2 that survived. I think that's a reasonable formula, a reasonable way to describe what's left after I cancel everything out. So the sum of the series is S infinity, which is arctan infinity minus arctan 0. So again, you can't just keep kicking the problem down the road. Because on the first example, it did work because the nth term, as we do the S infinity, the leftover part goes to 0. But here it doesn't. So what's arctan infinity? I over 2, arctan of 0. So the sum of the series is I over 2. Is there anything weird about a bunch of positive numbers adding up to pi over 2? Makes sense. So again, when you're looking at a telescoping series, you have to be careful. You might think, because everything gets canceled out, the sum is the survivors. But you have to do the analysis a little more so. Luckily, if you use partial fractions, it's always going to work. Things I want to talk about in this section. First of all, I do 1 plus 2 plus 3 plus 4. Does that converge or diverge? Diverge. And the problem here is the terms keep going up. So what if I just keep everything steady? So 1 plus 1 plus 1 plus 1. Does that converge or diverge? Still diverges? Agree with that? So when the terms are increasing, it's going to diverge. When they stay constant, it's going to diverge. So I'm going to do one where they're decreasing. That is here. 2 plus 1.1 plus 1.01 plus 1.001. Now the terms are decreasing. But you see that every term here is bigger than the corresponding term here. So does this guy converge or diverge? It's still going to diverge. If this adds up to infinity, this adds up to something bigger. What's the only number that's bigger than infinity? Infinity, because infinity is bigger than everything, right? Including itself. So not only do the terms have to be getting smaller and smaller, but it's the terms have to be going to 0. I'm adding infinitely many numbers together, and they better be getting, not only getting smaller and smaller, but they should get smaller and smaller, but also they should be getting closer and closer to 0. If they don't get closer to 0, then it's going to be bigger than the sum of a bunch of constant terms, and that's definitely going to diverge. So by the time the next exam comes around, I'm going to be giving you a bunch of series. You're going to decide for each series whether it converges or diverges, and then give me a good mathematical reason why you made the choice that you did. In one way, so a couple things we have so far. So you can say it's a geometric series, and R is in the right range. Another one is, we're going to give a name to this. So if the individual terms do not go to 0, then the whole series is going to diverge. copy the test for divergence down and see if you can apply it to that series right there. If I look at this piece, if I do the limit as n approaches infinity of n over n plus 1, what's that limit? Which, for the purposes of this example, is a number that's different than 0. And so if the terms do not go to 0, what can we say about this series? It diverges. Then we can actually give a reason why it diverges. As I use the test for divergence. And the cool kids write this as the TM. So it diverges by the test for divergence. And one more example. What if I put an alternator on it? Now, does this converge or diverge? It still diverges. Is the nth term going to 0 now? It gets close to 1, it gets close to -1, and closer to 1, and closer to -1. So it still diverges by the test for divergence. This series, 1 plus a half plus a third plus a fourth, and so on, is what does the test for divergence say about this? That is a trick question. Is the test for divergence says if something happens, then the series diverges. So can you ever use the test for divergence prove that something converges? So either the terms don't go to 0, and test for divergence tells us it diverges, or if the terms do go to 0, then the test does not apply. So you see that test for divergence does not apply. It's the most basic thing that has to happen to get a series to converge. Is we have to get the terms to go to 0. If they don't go to 0, we can automatically say that it diverges. And here's an example of a series where the terms do go to 0. There's different families of series that get their own name. So geometrics have all the series out there. We carved out the ones that have a certain property, we call those the geometric series. We carved out another group of series that we call a telescoping series. This is one of only a few series that actually has its own name. It's not a family of series. It's just this particular one. This is called the harmonic series. There's actually a reason. What's the most basic question we can ask given an infinite series? The first thing we want to know is whether it converges or diverges. what I'm going to do is I'm going to start breaking this into blocks. I'm going to keep the first couple. Let's do this in red color. In this block, I'm going to replace everything by the last term of the block. So 1/3 gets replaced by 1/4. And in this next block, I'm going to replace everything by 1/8. And in the next block, everything gets replaced by 1/16. Next one's going to get replaced by what? It's 1/3. Is the top series, the one I wrote in blue, bigger or smaller than the one that I have here? The top one's bigger. It's 1/3 got replaced by 1/4, which is smaller. 1/5 got replaced by an 1/8, and an 1/8 is smaller. 1/8 is also smaller than 1/6. Blue series is bigger than this. That's 2/4. How many 8ths do I have? 4 8ths. How many 16ths? 8. How many 32nds do you think I'm going to have?
16.
And conveniently, this is 1 plus a half, plus a half, plus a half, plus a half. Is what does this bottom series add up to? Maybe 1 plus a half, plus a half, plus a half, plus a half. What does it add up to? What is it? Oh,
Infinity.
infinity, right? So if I have infinitely many halves. So infinitely many halves. A half times infinity is still infinity. And then 1 plus the infinity is still infinity. So the smaller series adds up to infinity. So the harmonic series must add up to something bigger than infinity. What's the only thing that's bigger than infinity? Infinity. Because infinity is bigger than everything. So that means the harmonic series itself adds up to infinity. So does the harmonic series converge or diverge? It diverges. So what we have so far is if I give you a series, if it happens to be a geometric series, you know how to do a check to see if it converges or diverges. If the series telescopes, you know how to write out the process to see if it converges or diverges. If the given series, if the nth term does not go to 0, then we can automatically conclude that it diverges. And then finally, is the harmonic series happens to diverge. That's all you need to know for 11.2. 11.3 is kind of a fun section, like this.
Can I ask a question?
Yeah.
Why did you mention the harmonic series at all?
Oh, because what's going to happen? So, I don't know if you heard that. The question was, why did I even mention the harmonic series? And there are two reasons for it. One is students sometimes think that the opposite of this is true as well. If they don't go to 0, it diverges. Does that mean if they do go to 0, it converges? The answer is no. Second is we're going to be doing a lot of problems where we're trying to analyze a series, and we'll want to compare it to a simpler series. So the harmonic series is one series we have under our belt to compare it to other series. here is another series. I want to see whether it converges or diverges. What do we do now? It's an incredibly powerful technique. Especially leaving this in sigma form. 1 over square root of n. Is I'm going to look at the graph of f of x equals 1 over square root of x. And which looks like this. And then I'm going to think about each term of the sequence as a point on this graph. So instead of just looking at n equals 1, n equals 2, n equals 3, I'm going to place these on a graph. So this is 1 over square root of 2, 1 over square root of 2, 3, 1 over square root of 3, and so on. And now once I have that graph, we can use the entirety of calculus here. So this is going to be, it's a very cool trick. Is first I just interpreted these as numbers. Then they're y values for points on a graph, which are vertical distances. Now what I'm going to do is I'm going to turn these numbers into areas. So what's the area of this first box? Base times height. 1 over square root of 1. The area of the second box. The base is 1, the height is 1 over square root of 2. That third box is 1 over square root of 3. And this picture should remind you of something that we did in chapter 7, specifically 7.7. Remember we were doing the approximation rules? We had the trapezoid rule and Simpson's rule. Which rule are we doing here? The left-hand rule. So the way to look at this is we were trying to find the area under this curve. And instead, we divided it up into these blocks, and we used the left side to figure out the height of the rectangle. So one way to look at those numbers, remember they're just numbers and we write them as the series. And we can draw graphs where there are horizontal distances, graphs where there are vertical distances. Or what I'm going to do here is I'm going to think about these as the areas of the approximating rectangles for the left-hand rule. So I can think of this series left hand rule approximation for remember, when we did an approximation rule, there are 3 things I wanted you to be able to do. I wanted you to be able to apply the rule. I wanted you to tell me whether it was an underestimate or overestimate. And I wanted you to do an error analysis. So I just want you to do the second one here. Is the left-hand rule an underestimate or an overestimate? Over. So we get is that 1 over square root of 1 plus 1 over square root of 2 is going to be bigger than this integral. So what we've done is we're trying to analyze series, and we just were able to relate it to the integrals that we worked on earlier. Spent a lot of time integrating. And let me remind you how this works. As we looked at all the integrals in the form 1 over x to the p, and we just go from 1 to infinity. Remember this? Or do you want me to work this out by hand? Does this integral converge or diverge? It diverges. So remember, and we can talk about this more if you want. For integrals of this form, 1 over x to the p, if p is bigger than 1, it converges. And if p is less than or equal to 1, then it diverges. So particular example, p is 1/2. It diverges, which means that this integral adds up to infinity. The series adds up to a number that's even bigger than infinity. So the answer to my original question is the series converge or diverge? And drawing the right picture, as I can see the series represents something that's going to be a number bigger than the integral. The integral diverges, the integral is infinity, so that must mean that the series is infinity. So what we have so far, I'm just going to restate it. So it's given a series, 1 over square root n. I don't know whether it converges or diverges. Is I changed it to an integral. And I know that the integral diverges, so that means the original series diverges. So I explain why. Essentially, is we turn the convergence or divergence question of the series into a question about the convergence or divergence. And we already know, now we can use all of our integration knowledge to analyze the series. And the next one's a little bit more subtle. I'll show you how this one works. So I'm going to do one where the integral actually converges. I'm going to lead up to my series is 1 over n squared. And I'm going to compare this to the integral of 1 over x squared and try to see if the integral can tell me something about the series. Okay, first of all, what does the integral do? Yeah, so now that's a 1 over x to the p where p is bigger than 1. And this is what we know. So this is a finite number. And if we work it out, this actually turns out to be 1. So the sum of this series is a number bigger than 1. Is it possible that that series diverges? So is infinity bigger than 1? Is it possible that that series converges? So could it add up to just some number that happens to be bigger than 1? So if the only thing we know about the series is it's bigger than 1, the sum of the series is bigger than 1, that doesn't tell us if that's just a bigger finite number or if that's infinity. I'm going to draw a different picture, and that will allow us to use this, the fact that this integral converges to tell us something about that. Should be the story. The same type of picture. And so we're going to think about the terms of the sequence as y values on the graph of the function. Now, I'm going to draw a slightly different picture. So I'm going to draw a picture like this. Yeah, good. Very good. That's good. Actually, no one has ever brought that up. Good insight. I'm going to do something different. What's the area of the first box? Is that hard? So the base is 1, the height is 1/2 squared. That's 1/2 squared. Second box, the base is 1, the height is 1/3 squared. 1/4 squared. So it's my approximation. I've got 1/2 squared plus 1/3 squared plus 1/4 squared. You see that the boxes, I can interpret is at least that series as adding up all the boxes for a right-hand rule approximation for the integral. And how does the right-hand rule compare to the actual area? It's under. So we have is the sum of the series of underestimate. I spent a lot of time on that earlier. It's smaller than this. So what on the right-hand side, converge or diverge? This integral? Converges. I'll let you write everything down. So you can actually work out that this integral is 1. So back to my original series, is I've got that all this stuff adds up to a number less than 1. So is there any way I can add 1 to an, well, what's 1 plus a number less than 1? Could that be infinity? What we have is that from 2 on converges. And if I add 1 to a finite number, it's still going to be finite numbers. So that tells us that even when I add the extra 1 on, it converges. So what we have is if the integral converges, then all the terms added together except for the first converge. And adding the first onto that is still going to make it converge. And if the integral diverges, the series diverges as well. So that is worthy of another test. The name for that test is the integral test. We're given a series, and we've got a way to describe the nth term. The integral test says if I have a series, then I can switch it to an integral. and either the series and the integral both converge, or the series and the integral both diverge. So general question is, here's an infinite series. Figure out whether it converges or diverges. Another tool you've got is to change the sigma to an integral, and then see what happens. And then I have to be a little bit careful. There's certain mild conditions we need on the function, and it's going to be clear. Every example we have is the function is going to satisfy these. This is a math teacher. I can give you exactly the conditions. So first of all, we have to be able to integrate. And we integrate, we can only integrate continuous functions. So you could make a function that has a lot of jumps or breaks in it, but still agrees on the integers. Okay, another problem is, imagine that those are the actual terms of the sequence. So we're really just given A1, A2, A3, and we're trying to find what we call an interpolating function that nicely goes between those. So the function that we want it to look like that. But if you didn't restrict me, is I could make a function that does something like this. The area under the blue curve would tell us something about the convergence or divergence of the series. The area under the orange, even though it hits every point of the series, wouldn't tell us about the convergence or divergence. So we just want to say that f isn't a weird function like this, but f is more like that. The conditions we need: f of x has to be continuous, f of x has to be decreasing, and f of x has to be positive. I mean, every example that you have is this function. Actually, every example, that's a better way to say this, is I'm never going to give you a weird case like this. If it looks like, if you have this and it looks like you can integrate it, then it's the function will be like this. Let's try the harmonic series again. We already know the answer. I want to show you how this test works. So the harmonic series is the 1 over n. 1 plus a half plus a third plus a fourth. And the integral test tells us to turn it into an integral. And luckily, we can integrate 1 over x. What's the antiderivative of 1 over x? Log x. 1 to infinity. So that's log infinity minus log of 1. What's log of infinity? Infinity minus 0. And every time I give you something like this, I'm not going to put a function that ends up being one like yours. A function here, and if you can integrate it, then you can use the integral to answer the question. So does the integral converge or diverge? It diverges. And then, what the integral test tells us is the series and the integral stand or fall together. So if the integral diverged, what does that say about my original series? It diverges. And what test did I use? That was. And as I mentioned earlier, it's a later test we're going to get is we're going to take our given series and compare it to a simpler series that we know about already. So we know about integrals of the form 1 over x to the p. And there's the corresponding series that we're going to want to have. So give names to these. So if the series looks like this, 1 over a to the p. So some examples that we've seen so far are this guy, and this guy. Copy that down, and we'll talk about it. Anybody still working on this board? So for the top, what's the p? So it's a p series with p equals. And for this one over here, it's a p series with p equals. So based on the ideas that we just had, the series stands or falls with the integral. And we already know what happens here. Some values of p are going to correspond to convergence, and some values of p are going to correspond to divergence. So for the integral, which p's converge? P bigger than 1? And divergent is when p is less than or equal. So by the integral test, these same conditions apply to p series. So if you have a p series, all you have to do is check the value of p. If p is bigger than 1, then the series converges. If p is less than or equal to 1, the series diverges. I'm excited to show you some examples of this. Unfortunately, we have to take a break. Let's take 10 minutes, and I'll show you how to use the integral test using p series. So when the test comes around, you're going to get several questions of the form, determine whether the following series converges or diverges. And you're going to have to figure out the correct test to use. Luckily, in lecture or homework, is you're going to know exactly the topic that we're talking about. And so you'll know which test to apply. I want to know whether the series converges or diverges. What test do you think you should use? And even though we've just been talking about the integral test, we're going to convert this to an integral and see what happens. So the idea is you're experts, or you have a lot of tools to evaluate integrals. So I can use a trick from Calc 1, the W substitution, to make this log x is W, and then the 1 over x times dx is the dw. And remember, these are x values. So if x is 1, w is 0. If x is infinity, log of infinity is infinity as well. So the series and the integral do the same thing. They either both converge or they both diverge. And now I change this to a problem of an integral to evaluate. And you have spent a lot of time doing those types of problems. So this is 1/2 of infinity squared minus 1/2 of 0 squared. Good thing nobody's getting this and putting it on YouTube. So 1/2 of infinity squared minus 1/2 of 0 squared is what? So that means that the integral diverges. So what can you say about the series? Divergence. And then what test did we just use? Divergence. That's the idea there. Yeah, that's good. So it's, I think what you're getting at is log n is usually bigger than 1. And that means log n over n is going to be bigger than 1 over n. So if I add up all the log n's over n's, that's going to be bigger. Is this what you were thinking? Yeah. That's going to be bigger than adding up all the 1 over n's. This is the harmonic series. Does the harmonic series converge or diverge? Diverge. It adds up to infinity. So the only number bigger than infinity? And so another way to tackle this problem is to compare it to a harmonic series. In the next section, we're going to be doing exactly that. So we're going to have a series in question. We're going to compare it to a series we know already. And if things work out in the right way, we'll be able to say something about the relationship between the two. That's the right. And that's going to be one of the 2 tests that comes up. So with these infinite series, there's really 2 types of questions that you're going to be asked. So does the series converge or does the series diverge? And then if it converges, that means we know it adds up to some number, and we want to find what that number is. And then, this is going to be broken down into 2 parts. Sometimes we're going to know the exact value of the series, and sometimes we're only going to know an approximation. So an example where we know the exact value was one we did at the beginning of class today, 1 plus 2/3 plus 4/9 plus, if I add these infinitely many numbers together, we know what the answer would be. So what's the thought process to get this infinite sum? Now you see it's a geometric series. What are the 2 pieces? Well, the formula for the sum of a geometric series is a over 1 minus r. We derived that formula last class. What's the a in this problem? The r? The r is 2/3. That's how I get from one term to the next. Like we did earlier today, that answer is 3. So if the series looks nice, we can get the exact value. Just like with integrals, if we can find the antiderivative, we can get the exact value of the integral. Sometimes we're not going to have an exact formula for the sum. Instead, we're going to have to approximate. So let me give you some terms or some vocabulary that we use when we do these approximations. typical problem. And the way we approached this was we said S1 is A1, S2 is A1 plus A2, S3 is adding the first three together, and Sn is adding the first n. And so when I'm asking you to find the sum, I'm really asking you to find S infinity. And for our approximation, is we're going to say that Sn is going to be a good approximation to S infinity. The bigger the value of n, the better the approximation is going to be. So with integrals, we have 5 different ways to approximate the integral. With series, we only have one way to do it. Instead of adding the first infinitely many terms together, you're going to add the first 20 terms together and say that's close. So that part is called Sn. And then the error is going to be everything that we didn't add. So the error, we give a name to that, we call that R sub n. So that's the remainder after what's left of the series after we compute the S. This is one place you want to be careful of, is what is the first term of Rn? An plus 1. See this in action. What's the first term of R4? A what? And in action is for this series, all our series are in. Not supposed to say otherwise. So for this series, 1 over 1 squared plus 1 over 2 squared is I want you to circle R5. What's the first term of R5? A6. R5 is going to start right there. Let's remember, it's the S's that we care about. So S5 is we add up from 1 to 5, and then R5 is what's left over. It's a little bit confusing. R5 starts at A6. So once we have an approximation method, do you remember the 2 things we wanted to do? So it's an underestimate or overestimate. And right now, all our series only have positive terms. So is it going to be under or over? Under, right? So I'm trying to get the answer for adding infinitely many positive numbers together. I skip infinitely many positive numbers. So that means that the one I get is going to be under. So Sn is going to be smaller than S infinity. It's an underestimate. And then what's the third thing we need to do with an approximation method? Yeah, by how much exactly? We need to be able to say something about the error. So for that same picture that we drew for the left-hand rule and the right-hand rule, is I'm going to use that same picture for just the Rn term, for the error. Is I'm going to interpret this error as a left-hand approximation to some integral and a right-hand approximation to some integral. And then that integral will tell us something about the error. That R sub n is the series we get after we already calculated the Sn. For each of these, imagine these are points on a graph. Interpolating function is y equals f of x. I'm going to draw the same picture over here. I'm going to erase over on the right. So we do the same thing. I'm going to draw the picture twice. One time, this series is going to represent a left-hand rule. And one time, the series is going to represent a right-hand rule. First, it's just given to us as numbers. If I draw this picture, is those numbers represent these vertical distances. Then I can use these as the left side of a rectangle to give you a left-hand approximation to the integral. A plus 1, A plus 2, A plus 3. So one interpretation of those numbers is the areas of all these boxes that are an application of the left-hand rule of the integral. And another interpretation is I can use these as the right-hand side of a rectangle. And that's going to give me the right-hand rule for the integral. So here is the left. Is this left side going to represent an underestimate or an overestimate? It's an overestimate of this area. And so where does that integral start? At n plus 1. Just copy that over here. Is we get that remainder term, the r sub n, is going to be bigger than the integral from n plus 1 to infinity f of x. I'm going to make a similar statement about that side. So now, this an plus 1 plus an plus 2 is representing an approximation using the right-hand rule. Is that going to be an underestimate or overestimate of some integral? It's going to be an underestimate. It's an underestimate of what integral? That would be the one where we start integrating out. So what we have from the second picture is that the r sub n is smaller in the integral from n to infinity. And traditionally we write these for compound inequality. So my r sub n is bigger than the integral from n plus 1 to infinity and smaller than the integral from n. So this is how we can use an integral to say something about the error that we get when we try to do it, when we do an approximation. A little bit of history. Every generation has its unsolved, hardest math problems. And all the top mathematicians in the world work on these problems. And every once in a while, someone figures one out, and then they become famous, or even more famous. So after calculus was invented, as people got interested in this series, does this series converge or diverge? Converge, how do you know? It goes closer to 0. So does the harmonic series. It's a p series, and p is 2. So then, the interesting question was to find the sum. And Euler, in the early to mid 1700s, worked out the answer to this problem is pi squared over 6. There's an interesting aside. In the year 2000, mathematicians got together and decided what they thought were the most important problems for our generation. And to make it interesting, is they put $1 million bounty on each problem. So if you can solve one of those problems, it will pay you $1 million. Because there's a mathematician who lived in Moscow, and he wasn't working for a university, he just immediately had a job. He lived in a small apartment with his mother, and he was working hard on one of the problems and actually figured it out. So the committees, they looked at his work, and said, yeah, you're right, you figured it out, here's your check for $1 million. And you know what he said? He said, you do not do mathematics for money. So he refused the $1 million prize. I have no idea what his mom said. So, a problem that nobody knows the answer to.
They just check over, right? They don't try to do it themselves.
No, they just, so somebody says, here's how to solve the problem, and then people read through it, hopefully. It's the person who had the right solution. So, to this day, nobody knows what those add up to. So when Euler was trying to figure this out, he would add a bunch of the numbers together, and then he'd get the decimal approximation. He'd say, you know what, that decimal looks a lot like pi squared over 6. Maybe I should start trying to prove that that's what it equals. So if I was working on this problem, let's call this S infinity. Here's my approximation to S infinity. I'm going to add the first 10 together. So do you see that this term is already 1/1000th, 0.0001? So they're already pretty small. But out of the infinitely many terms I'm supposed to add together, how many did I get? Percentage-wise, what's 10 out of infinity? 0, right? I really didn't add. I had it already been done. So I want to know how close is that? On one hand, that's a pretty small term. But on the other hand, is, I don't know, missed a lot of numbers. Because luckily, we can answer the question, we can answer the question about the error by evaluating the integral. So which S is this? S1, S2, S10. And so the error for S10 is R10. And from our relation here, we know that R10 is smaller than the integral from 10 to infinity. In this case, 1 over x cubed dx. I'll write down the correct antiderivative. If you have questions about how I got that, let me know. So that is 1 over 300. Whereas a decimal, point 0.003333. Oh, actually, you know what? Actually, work this out. This is 1.1975. I want to know, what should I round this to? Do you remember what 2 decimal places means? 2 decimal places that can be phrased in terms of something about the error. So accurate to 2 decimal places is the same as the error is smaller than 0.00. So you see that our error we know is smaller than 0.003. So the error is smaller than 0.005. In other words, this approximation is good to 2 decimal places. So in your science classes, you talk about how to round to the significant digits, significant figures. Is to 2 decimal places, we know that S infinity is 1.20. Second type, is that good so far? And I'm going to, yeah. Oh, I just worked it out. So these are 10 numbers I have to add in my calculator. I just did that before the lecture started.
Could one theoretically find the limit of times S sub infinity by using a computer?
So it's our only way to find, the only way that we know right now to find S infinity is to actually add the infinitely many terms together. So that's going to be infinite numbers to keep track of, and we'd have to add infinitely many things.
Well, like, could you do with a computer? Because they also use computers to calculate pi.
To billions of digits, but not all the digits.
Yeah, could you theoretically like just let a computer do the work and keep going wherever?
Oh,
and
and
see where
I can get any number of decimal places you want, but I cannot get, nobody knows how to get the exact answer. So this is a nice way to represent what the exact answer is. I mean, I could get as many decimal places I want for any of these, but what we're really looking for is a nice formula like this to represent the actual answer. integral? I mean, so do you see the difference between knowing all the decimal places and being able to compute up to any particular spot? You let's put it this way. I believe that whatever decimal place you need to get the answer accurate to a billion decimal places, you can do that. But solving the problem is finding a simple expression similar to this that this adds up to. So, does 1.20, something close to 1.975, remind you of any number? Pi squared over 6, or pi squared over 9, or pi cubed over 12, or something. So 1.20 is all we're sure about. So my next question is, how many terms do we have to add up in order to get to 3 decimal places? What I want to do find the smallest n. Let's see. 3. So 3 decimal places can be translated into a statement about error. So 3 decimal places as a statement about error is what? Is error smaller than 0.0005. So this is always true. The error is always smaller than the integral from n to infinity of 1 over x cubed dx. And then what I'm going to do is I'm going to find a value of n. So the bigger n is, the smaller this integral. I'm going to find a value of n that makes that true. So what I have is I'm going to have a less than b, and b is less than or equal to c. So what does that tell you about the relationship between a and c? A has to be smaller. So if I can pick the n that makes this happen, and we just showed that that always happens, then I'll have my error smaller than 0.000. So let's work on that part of it. What I need to happen we did this integral already. So that integral is antiderivative, plug in infinity, plug in n, becomes 1 over 3n squared. And then, as in your arithmetic class, we talked about how to change decimals into fractions. 0.0005 is 1 over 2,000. Gentle reminder, we did this when we were analyzing errors for integrals. If I take the reciprocal of both sides, what happens to the inequality sign? As long as they're both positive or both negative, it flips. So I get that n squared is greater than 2,000 over 3. Or n is greater than or equal to the square root of 2,000 over 3. And the calculations that I do back. That's 31.62. So what does n represent? So n is the subscript on the s of n, which is the number of terms I need to add together to be accurate to 3 decimal places. So n can't be a decimal. Either use 1 term or 2 terms or 7 terms or 20 terms. So what is this? What is it? 32.
Is
The
that
smallest n is the answer. Is n equals.
wait, the 33 factorial 62?
No, 31.62. How's that?
Yeah.
And then there's one more trick I want to show you, and this is when we can get an upper bound, where we also have a lower bound on the error, is we can do something to get a better estimate. We won't be able to tell whether that estimate is an overestimate or an underestimate, but we'll be able to use it to get a better one. So I am looking at Euler series. So imagine that instead of adding those infinitely many numbers together, I got 1.4236. Is that an underestimate or an overestimate? What is it? Under, yeah. So it's, the correct answer would be adding those infinitely many positive numbers together. And I stopped at 4. But, which S did I use here? So, which R is the remainder for S4? Is it R4 or R5? R4 is the remainder for S4, which starts at R at 8.5. So we know that R4 is between two integrals. And I want you to take a moment and decorate these two integrals with the appropriate lower bound. Gentle reminder about the error bounds. R is smaller than the integral from n to infinity, and bigger than the integral from n plus 1. So for our particular example, what's the lower limit on the right? 5, and the lower limit on the left? So we know R4 is between 0.20 and 0.25. So back to my original series, there's the S4, and R4 is what I have left. Huh? No. So remember, R4 starts at the 5th term. So R4 is the remainder for S4. So what happens if I add S4 plus R4? If I add those two together, what do I get? I get the entire sum that I'm looking for, I get S infinity. So I know this, and then if I add S4 to all of this, well, S4, we worked out as 1.4236. So if I add 0.2 to that, S4 plus R4 is the sum of the entire series. That's the S infinity. And then this is 1.67. So by having that upper bound and lower bound for the error, is I've got a range of possible numbers that the answer can be. That's not too surprising. You've got the 1.4 as my estimate. And then, as I knew that was an underestimate, and the actual value is somewhere between 1.6236 and 1.6736. So let me draw a picture of that. The answer to my question is going to be some number in this range. If I had to guess one number, what would be the best guess? The best approximation is going to be the one right in the middle, which is the average of those two. So I don't know if that's an underestimate or overestimate anymore, but that is going to be a lot closer than my original estimate. So knowing the range of the error, so actually let's put it this way. If I knew my approximation and I knew the error exactly, then I would know the exact value I'm looking for. Instead, I know my approximation, I can compute that, and I've got a range of possible values for the error. That gives me a range of possible values for the real value. And then, if I had to pick one number as an approximation, it's going to be one number in this range, and the best I can do is by picking the middle number. You guys excited to go on to the next section?
No.
You really feel mathed out? Right.
Okay.
So given that I calculated S4 already, get a good estimate based on it.
Okay.
So one thing I learned, you guys know Robert's Rules of Order? So in the 19th century, there was an engineer who had to go to a lot of dumb meetings. So he just sat down and figured out how would you engineer a meeting. And so what he did was he figured out how to get people to not talk over each other. You have a chairman, or chairperson of the committee. And then the chairperson runs the committee, runs the meeting. And then what people can do is they can propose motions. So I, and the chair can do it or anybody else, propose that we adjourn this class right now. And then, have you guys been in any meetings on this yet? So then what happens is we have a call for discussion. So this is your chance to discuss the motion that I proposed. Would anybody like to discuss this? Oh, no, actually, before we do that, because we need somebody to second the motion.
I second the motion.
Second.
Okay, you got a second, you got a third, I think, 2 seconds. Then it's time for discussion. So we discuss the motion.
We agree.
And you can only talk to me. You can't talk to each other. You have to address the chair.
I agree with this motion.
Okay, good. And then we're going to go for a vote. If you're in favor, you vote aye. So the aye votes.
Aye.
Aye. Opposed? You vote nay. And then abstain, that means you don't want to vote. So the ayes have it, class is dismissed. Woo.